AC generators. What is an AC generator? AC generator is a device which converts mechanical energy into the electrical energy using the principle of electromagnetic induction. Before seeing what is a generator, let's see what are the laws regarding all that. So, electromagnetic induction. What is electromagnetic induction? It is the phenomenon by which EMF or voltage is produced or induced in the coil, in this coil, if there is a change in magnetic flux linked with the coil. Now, Faraday studied some experiments. We need to know this all. So, I have just included these slides. Let's see his first experiment. He proved that when the strength of magnetic field is varied, then only induced current is produced. A ammeter is connected in the loop. Here, an ammeter is connected. The ammeter deflects when the magnet is moved towards the wire. If we move it towards the wire, then it will show deflection. Now, his Faraday's second experiment, he proved that when the current is passed through the iron rod, it becomes an electromagnet. He noticed that whenever there is a relative motion means there is a vibration between the magnet and the coil. Between a magnet, here is a magnet and here is a coil. Whenever there is a vibration or relative motion, then what happens? Induced electromagnetic force is produced. When the magnet is rotated about its axis, no electromotive force is observed, and if the magnet is rotated about its own axis, then the induced EMF is produced. Thus, there is no deflection in the ammeter when the magnet is held stationary. Whenever there is a motion, either the magnet should be in motion or the coil should be in motion. If there is any motion in these two things, then electro EMF is produced, electromotive force is produced. If the magnet is stationary and this one is also stationary, then there is no change in deflection in ammeter, means there is no current, so no EMF is produced. In the third experiment, he noticed that the galvanometer does not show any deflection and no induced current is produced in the coil when the coil is moved in a stationary magnetic field. The ammeter deflects in the opposite direction when the magnet is moved away from the loop. Now, what are the two Faraday's law of electromagnetic induction? These two are very important and you should by heart it for your further use. Whenever there is a change in magnetic flux, linked with the coil, an EMF is induced. The induced EMF lasts so long the change lasts. There is a change in the magnetic flux linked with the coil. Second one, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil. If the magnetic flux changes at a fixed rate, a steady EMF is produced. So this depends upon the rate of change. If we move it slowly, then a slow EMF is produced. If we move it fast or there would be rapid motion, then the change is rapid, then EMF is also high. Let's see what is the factors affecting the magnitude of induced EMF. As we have already discussed, what is induced EMF? Change in magnetic flux of each turn into number of turns in the coil by time in which the magnetic flux changes. Thus, for a given coil and magnet, it depends upon two factors. First is rate of change of magnetic flux with each turn. Second one is the number of turns. Here as we can see. First is change in magnetic flux. Second one is number of turns. Now there will be an induced EMF whenever there is a relative motion between coil and magnet. There will be an induced EMF. So there will be an induced EMF, but how to determine the direction of induced EMF? The direction of induced EMF, and hence the direction of induced current, depends on whether there is an increase or decrease in magnetic flux. It can be obtained by these two rules. One is Fleming's right hand rule, second one is Lenz's law. Let's see what are those laws. Fleming's right hand rule states that stretch the thumb, central finger, and forefinger of your right hand mutually perpendicular to each other, as shown in this figure. If the forefinger indicates the direction of magnetic field and the thumb indicates the direction of motion of conductor, then the third middle finger indicates the direction of induced current. Now, what is Lenz's law? It states that the direction of induced EMF or induced current always tends to oppose the cause which produced it. So, the direction of induced EMF or induced current will always be in the direction so that it is like opposing the cause which produced it. Now, let's see what's the AC generator. AC generator is a device which converts mechanical energy to electrical energy using the principle of electromagnetic induction. Electromagnetic induction is what we have studied earlier. Let's see, this is a elementary diagram of a AC generator, a simplified diagram of an AC generator. Where is AC generator used? Practically, it is used whenever you get a power cutoff at your home. In earlier days, you must have seen an AC generator. Whenever we use an AC generator, we can get light or power during cutoff. So another place where it is used is in windmills, in hydroelectric power, for hydroelectric power generation near the dams. AC generator is used, and this is a simplified version of AC generator. Let's see what are the parts of an AC generator. As you can see this diagram, the first one, second one, third one. This third diagram is directly from the Selena book of ICSE class 10. So first let me explain this 3D dimensional figure. The same thing is here. There is a north pole and south pole. This is a field magnet. Here also it is given field magnet. It is named as field magnet. Then what it contains? Two coaxial slip rings. As you can see here, there are two coaxial slip rings here. Slip ring S1, slip ring S2. Then what we have? Two carbon brushes B1 and B2. Here B1 and B2. What are they? They are made up of carbon. Here carbon is used for brushes. One more thing, children, this carbon, one end of the carbon brushes is connected to the slip ring and another end is connected to the load. Similarly, for this brush, one end is connected to slip ring S2 and another end is connected to load. But this the one end which is connected to the slip ring is just gently pressing it. It is not totally fixed. Here also it is just gently pressing the slip ring S2. It is not totally fixed. And it contains an armature coil. Here it is shown half in red and half in blue. Here the total one is in black color. Here this armature coil is a insulated wire which is insulated, and which is inside it. Here you can see a magnet, soft iron core is present. Here also actually in everything the it's this insulated armature coil is wound around a soft iron core. So these things are the main parts of AC generator. One is field magnet, which is a concave magnet. Then the armature coil, A, B, C, D, the slip rings, then the brushes. Now let's see how does it works. Now the working of AC generator is shown in this figure. Let's see. Initially, let the plane of the coil be perpendicular to the magnetic field. Now this plane of the coil, this is the plane of the coil. Now the coil is perpendicular to the plane of the magnetic field. How is that possible? See, magnetic field is in the direction of north to south, indicated by this yellow lines. Now what happens? The plane of the coil is perpendicular to the magnetic field. So initially theta is equal to 0. Theta is taking the angle, changing angle. Now initially if it is in this position, means it has not changed any angle. So theta is 0 here. In this position, the arm AB of the coil is below the plane of paper. This color shows the arm AB and it's below the plane of the paper, while CD of the coil is above the plane of the paper. The red color mark shows here the CD. The end A, this one is the end A. This one is the end A and this one is the end B. The end A of the coil is connected, end A of the coil is connected to slip ring S1, and the end D, this one is the D, is connected to the slip ring S2. The brush B1 touches the slip ring S1, the brush B1 touches the slip ring S1, and the brush B2, this is brush B2, touches the slip ring S2. No EMF is induced in the coil when it is at rest. Now, is there any motion? It is just placed perpendicular to the direction of magnetic field. Now, there is no EMF induced in the coil when it is rest. Why there is no EMF? Because according to electromagnetic induction, it states that whenever there is a relative motion, then only what happens? Whenever there is a relative motion, then only the EMF is produced. And since it is at rest, so there is no EMF induced. Whenever there is a change in the number of magnetic field lines linked with the conductor, an EMF is developed between the ends of conductor, which lasts as long as there is a change in the number of field lines. So see here, maximum number of field lines are entering this coil. So there is no change in magnetic field lines. So the EMF induced is 0. Now this was the first position. Suppose there is an axle here, or there is an handle here, which is not shown in this figure. There is an handle here. So what we will do, we will rotate it clockwise. It was first in this position A, and now we have rotated it by 90 degree. So now what happens? As we can see in this figure, now the magnetic field lines is perpendicular to the plane of the coil. So what happens? In the second one, magnetic field lines is perpendicular to the plane of the coil. Now applying, now what happens in this condition? The number of magnetic field lines crossing this coil becomes 0 here, as it is already parallel to the magnetic field. So when the field lines crossing here becomes 0, now in this case the EMF induced is maximum. See here, you can see the graph shown in below. See, first it was 0 in this position, perpendicular position. We saw that the voltage induced was 0, but when in this position here, the magnetic field lines crossing or cutting this one is 0, and so the EMF induced is maximum. Then again we will rotate it by 90 degree. What happens then? If when we rotate it 90 degree, this part, this red color part goes downward and this yellow color part comes upward. Now in this figure what happens? Again the field lines or magnetic field lines entering this coil becomes maximum, and here what, the magnetic field line is perpendicular to the plane of the coil. Here the maximum flux enters through the coil. So what happens? The EMF induced is 0. So in this figure what happens? Maximum flux enters the coil, so EMF induced becomes 0. So at this position, point C, again it becomes 0. Now when the coil is further rotated, what happens? Further rotated means this red color part goes this side. It has come in this figure, as we can see, it has come this side, and this black color part has come towards the south pole. The magnetic flux in this diagram of D, let's see. The magnetic flux linked with the coil decreases. Magnetic flux linked with the coil decreases. Why? Because the magnetic field is parallel to the plane of the coil, and the EMF again increases to the maximum value. Again what happens? Here we have also seen the same thing. Here since the magnetic flux linked with the coil decreases, so EMF becomes high. Similarly here the EMF has become high, maximum, but in the opposite direction. But what happened here? What we saw, that the red color part was near the south pole. Here what we are seeing, the red color part is near the north pole. So here the EMF is maximum but in the opposite direction. When the coil gets turned by 270 degree from its initial position, here let's calculate. First it was in 0, here 90 degree plus 90 degree, 180 degree, again 90 degree. So total 270 degree turned. When the coil gets turned by 270 degree from its initial position, as shown in this figure, the EMF induced in the coil is maximum because the rate of change of magnetic field is again maximum at this instant. Now the arms of the coil AB and CD have interchanged. Earlier it was down, the arms were this side down, and now it has interchanged. The AB has become this side, right? Have interchanged their position. As a result, an induced current flows in the coil. For this diagram D, I am saying an induced current flow in the coil in the direction DBCA, that in the external circuit from the brush B1 to B2. So here as we can see, just remember that the since here the direction, the red color part of the coil was near the south pole, and here the red color part of the armature coil is towards the north pole. So the direction as it has changed, but the flux is parallel. The maximum, the flux here, the flux cutting or passing through the coil becomes 0. So the induced EMF is maximum, but it is in the opposite direction. Similarly here what we can see, here again perpendicular, the diagram again coming back to the position, this position 90 degree, again turn 90 degree. What happens? Again maximum flux enters through it. So what happens? The induced EMF is 0. So this graph shows what is the main thing, purpose of this whole lesson. In AC generator we know that whenever there is a maximum, whenever the magnitude of the induced EMF becomes maximum, the magnitude of induced EMF or induced voltage becomes maximum when the magnetic flux linked with the coil reduces to 0. Here how much coil can pass, how much magnetic field passes through it? No. reduces to minimum. So whenever magnetic flux passing through this coil becomes zero, then what happens? The induced EMF is maximum. And here what happens? All the magnetic flux passes through it. So magnetic flux is maximum. So induced EMF is minimum. Second one, the induced EMF becomes zero. Seeing this diagram, the induced EMF becomes zero when the magnetic flux linked with the coil is maximum. So magnetic flux linked with this coil is maximum. Here also maximum amount of flux passes through. So induced EMF in this case and this case becomes zero. Whereas here the minimum amount of magnetic flux passes through. And so here the induced EMF is high. So hope you have understood this one. Now frequency of alternating current. In the previous figure what we saw that this induced voltage. How does it happens? Because it is directly proportional to induced current. However, the current also flows in this direction. First it flows in positive direction. Again for the next half rotation it flows in the negative direction. So frequency of alternating current. Alternating current is what? Its polarity changes. Magnitude remains same. Magnitude is plus 5 volts, suppose. Here also minus 5 volt. 5 is the magnitude. So magnitude remains same, but the polarity here it was positive. In the second half of the rotation it was negative. So alternating current is one whose magnitude remains same, but the polarity varies. Let's see. In one complete rotation of the coil, we get one cycle of alternating EMF in the external circuit. Thus, the alternating EMF has the frequency equal to the frequency of rotation of the coil. If the coil makes n rotation per second, the magnitude of induced EMF at any instant is given by, this is a formula which you have to remember, E is equal to E0. E0 is actually the magnitude, sine 2 pi nt, where E0 is the maximum EMF value or the magnitude. I is equal to, similarly current is expressed as I0 sine 2 pi nt. I0 is the maximum current value. How can this E0 of EMF can be increased? By increasing the number of turns of the coil. Second, increasing the area of cross section of coil. Third one, increasing the speed of rotation. This E0 is 2 pi n BAN. No need for now, but for higher classes you will be studying about what is E0. E0 is actually 2 pi n BAN. B stands for here magnetic field, area of the coil, A for area, and N is the number of turns of the coil. So 2 pi n BAN, it is equal to what? 2 pi n BAN. So it is depending on magnetic field, area of cross section, and number of turns of the coil. Let's see now what is the distinction between AC generator and DC motor. Earlier I have made a video on DC motor, working of DC motor, and now today I have explained you about AC generator. So now let's see what is the difference between both of them. A generator is a device which converts mechanical energy into electrical energy. Here mechanical energy is getting converted to electrical energy. Now in DC motor what happens? Remember the fan, table fan? The DC motor is a device which converts electrical energy into mechanical energy. Now generator works on the principle of electromagnetic induction, and DC motor works on the principle of force acting on a current carrying conductor placed in a magnetic field. Now in a generator, the coil is rotated in a magnetic field so as to produce electric current. In a DC motor, a current from a DC source flows in a coil placed in a magnetic field due to which coil rotates. A generator makes use of two separate coaxial slip rings, whereas a DC motor makes use of two parts of a slip ring. It is half circled here for DC motor, and here we use complete two circles, right? Okay, thank you. If you like my video, please subscribe to my channel.